All right, folks, today we're going to take a look at Newton's second law, and we have looked at the basis of this law already, but we're going to set up a little bit of a demonstration here with a rolling cart and some hanging masses. It's a pretty traditional setup to demonstrate Newton's second law, but very quickly I'm going to review what it is. On the board, I have the base form of the equation for Newton's second law, which states that force is equal to mass times acceleration. And this, in terms, would also be like the resultant net force on a vehicle or an object. In this situation, we're talking about a rolling cart. So the total force acting on it's going to be the net force, which will be the sum of the, let's say, positive force pulling this cart down the track. And in this situation, the force that we're going to be using is a hanging mass. So the string will be weighted with these brass masses, and the mass times the acceleration of gravity pulling down on this is what's actually going to produce a force to pull the cart. There will be some friction going in the opposite direction. We're trying to minimize that as much as possible, but when we do the actual calculations to predict what the acceleration of this cart should be relative to the actual timed distance and time to get velocity and calculate acceleration that way, it's assuming the net force on it. So we may not necessarily know the actual frictional force pulling the other way, but what we probably should notice is our predicted values would maybe show the acceleration to be a little bit greater than what we actually get, because in a perfect world, there is no friction. There's obviously friction between the surface of the wheels and the air resistance going by also. So here's kind of what we're going to be looking at. We know force is equal to mass times acceleration. What we're going to try to do is compare the real data for calculating acceleration using the distance and time to the predicted value for acceleration using our measured force, which is going to be the force of this pulling down divided by the mass of the cart. So we can directly figure out the mass of the cart in kilograms, and we could kind of predict, again, without friction, what the acceleration of the cart should be. So with that said, a couple of things we're going to look at is how we're going to keep the mass of the cart the same. So the only thing that we're going to have as a variable is we're going to change the force a couple of times and then do the calculations for acceleration. All right. So with that said, we'll move on and I'll set up some more examples.